The last part of Lecture 11 talks about different methods to solve for enthalpy and entropy. Here is a sample problem. We want to find delta H naught and delta S naught for a reaction that has an equilibrium constant of 61 at 336 Kelvin and 1200 at 452 Kelvin. Here is how you would do that. First, we use a formula to get delta G naught from the equilibrium constant at two temperatures. So working with the data at 336 Kelvin, I know that delta G naught equal minus RT natural log of K. I would like this value in units of kilojoules per mole, so I will use my 0.008314 R. The temperature is, of course, 336 Kelvin, and I have the natural log of the equilibrium constant. So when I multiply all this through, I have the delta G value at 336. I'm going to repeat the process at 452. So now I have two delta G naught values at two temperatures. So what can I do with these values? Not only does delta G naught equal minus RT natural log of K, but it also equals delta H minus T delta S. Now when you go to advanced chemistry courses, you will notice that delta H naught and delta S naught change with temperature, but they don't change very much. So it is a reasonable assumption to assume that delta G naught at some temperature is equal to the delta H naught at 298 minus that temperature and the delta S naught at 298. So if I use my delta G information at two different temperatures, I have two equations and two unknowns. Here's my first equation at 336. I calculated this value and I know it equals delta H naught minus 336 Kelvin delta S naught. The same is true for delta G naught at 452. I solved for a value and it's going to be equal to delta H naught minus 452 Kelvin times delta S. Now what I will do is subtract one equation from the other. That means I will have delta H at 298 minus delta H at 298, which cancels out to 0. I will also have minus 11.48 minus a minus 26.64, so that would be a plus 15.16 kilojoules per mole. And I will have minus 336 Kelvin minus a minus 452 Kelvin, both of which are multiplied by delta S naught. So the difference there will be 116K times delta S naught. So dividing, I can come up with the value of delta S naught in either kilojoules per mole Kelvin, or as delta S naughts are more commonly reported, as 130 joules per mole Kelvin. Now I've solved for delta S naught. How do I solve for delta H naught? Well, I just need to plug that value in to one of my two equations. So I will use the delta G naught at 336 that I calculated before using the equilibrium constant and set it equal to delta H naught, which I do not know, minus 336K and my value of delta S naught. And when I solve for that, I now have delta H naught at 298 as an estimate 32.43 kilojoules per mole. I didn't have to use the equation at 336. I could have used the equation at 452. I will get the same answer either way. So if we wanted to take this one step further and get the equilibrium constant at 200 degrees Kelvin, I can use that same equation where delta G naught is equal to my newly solved value of delta H naught minus 200 Kelvin times my newly solved value of delta S naught And I can find out that delta G naught at 200 is 643 kilojoules per mole. I can now use the equation, the equilibrium constant is equal to E raised to the minus delta G naught divided by RT. So I sub my value of delta G naught at 200 in there and divide by R and the temperature to get the equilibrium constant of 0.0209. So let's try a practice problem. We are going to look at the equilibrium between two NO2 gaseous molecules and N2O4 as a gas. We are given equilibrium constants at two temperatures. At 25 degrees Celsius, the equilibrium constant is 8.81. At 80 degrees Celsius, the equilibrium constant is 0.227. First, we're going to solve for delta S naught in joules per Kelvin. So our strategy here is to first get delta G naught at two temperatures using the formula delta G naught equal minus RT natural log of K. So I've set it up for you for delta G naught at 25 degrees Celsius. We have a minus 0.008314 kilojoules per Kelvin mole. Our temperature of 25 degrees Celsius, we are of course going to correct to units of Kelvin by adding 273.15 times the natural log of 8.81. So that turns out to be minus 5.394 kilojoules per mole. So your job is to repeat this at 80 degrees and solve for delta G naught at that temperature. Our next job is to subtract the two equations, delta G naught equal delta H naught minus T delta S naught at two temperatures. So I've set up the first one for you, delta G naught at 25 degrees Celsius, which we have solved for as minus 5.394, is equal to delta H naught minus the sum of 25 and 273.15, so that's 298.15 times delta S naught. And of course, it wouldn't be chemistry if I reminded you of the units. Our delta G naught is in kilojoules per mole, and our temperature is in Kelvin. So your job is to set up the second equation for delta G naught at 80 degrees, and then subtract one equation from the other. So you'll get a value for the difference between the delta G naughts. The delta H naughts will cancel, and you will have some temperature times delta S naught. So your job will be to divide what's on the left side by what's on the right side. Now, keep in mind, you're being asked for the answer in joules per Kelvin mole. So make sure you have this answer, and whatever you get, remember to correct your kilojoules per Kelvin mole to joules per Kelvin mole. The next question asks, what is delta H naught in kilojoules? And the implication is that is kilojoules per mole of the reaction written. So from part A, you should now know the value of delta S. You can use the delta G equation at either temperature. I'm just going to use the delta G naught at 25. So just substitute in your delta S naught value that you had on the previous page. Of course, don't forget that this delta S that you substitute would best be in kilojoules per mole, since your delta G is in kilojoules per mole. And once you do that, you should be able to solve for your delta H naught at 25 degrees Celsius, which is also your delta H naught at 80 degrees Celsius or any other temperature, because our assumption is that delta H naught is temperature independent. Our next question asks us to identify the flip point of the reaction. This is when delta G naught changes sign. So it either changes from plus to minus or minus to plus, which means it has to pass through zero. So I remind you that if delta G naught is equal to 0, if we rearrange this, the flip temperature is going to be equal to delta H naught divided by delta S naught. Now let's think about units for a minute. We should insert our values of delta H naught in kilojoules per mole and delta S naught in kilojoules per Kelvin mole, which means the answer we get is going to be in units of Kelvin. So I remind you that Kelvin is 273.15 plus Celsius. So if we want our answer in Celsius, we need to subtract 273.15 in order to get 2 degrees Celsius. Now, I will give you a little bit of an extra hint on your answers. Your values for delta H naught and delta S naught should both come out to be negative. So that means at low temp, when delta H is in charge, delta G should be equal to delta H, so it should be a negative sign. Delta S is negative, but the entire term, which is known as the high temp term, is minus T delta S. So that means at high temp, delta G naught will be a minus times a minus, so it will be greater than 0. Of course, you know that less than 0 means spontaneous, and greater than 0 means non-spontaneous. So it is below the temperature we determine that the reaction will be extensive, which is similar to saying it is spontaneous in the forward direction at standard state. Now let's look at non-standard conditions. So suppose we are under conditions at 25 degrees Celsius where the NO2 is 0.5 atmospheres and N2O4 is 0.73 atmospheres. We want to know what is the value of Q and is the reaction spontaneous in the forward or the reverse direction. So I remind you that Q is the reaction quotient, so it will be just like K, but not at equilibrium. So we will have products divided by reactants, or the pressure of N2O4 over the pressure of NO2, and don't forget to square that because it has a 2 as a coefficient. So I will let you solve for this value of Q. The other question we need to ask is, does the reaction go forward or in reverse? Well, let's compare Q to our K value at 25 degrees Celsius. K is equal to 8.81. So I hope you remember, if K is greater than Q, the reaction goes forward, and if K is less than Q, the reaction goes in reverse. And finally, we'd like to know the free energy change not at standard state under these conditions that have been defined. So I remind you that delta G is equal to delta G naught plus RT natural log of Q. So delta G is equal to that minus 5.394 kilojoules that we got in part A for the reaction at 25 degrees Celsius. So this is a simple matter of adding R times T times the natural log of the Q value that we got in part D. So you should be able to solve that. And just a reminder that conceptually, the answers for part D and part E should be the same. If you decided in part D that the reaction should go forward, then you also should have a negative free energy change. If you decided in part D that the reaction should go in reverse, then you should have a positive value for delta G. So I hope that helps you solve this series of problems.